Okay, so welcome back to another video. So here's a question from the 1985 Putnam Exam marked as question B5, and that is just evaluate this improper integral. The integral from 0 to infinity of t to the power -1/2, or 1 over square root of t, however you want to look at it, multiplied by e to the power -1985 times t plus t inverse dt. And I didn't write this down, but this was also written in the question, and it says that you can assume that the improper integral -infinity to infinity of e to the -x squared dx is equal to square root of pi, the Gaussian integral value, in other words. So you might be thinking, isn't this just in the form of a gamma function? Well, you want to be careful there because, well, for one, it does set the bounds that, yes, it satisfies that it's from 0 to infinity, and we have that it's a variable multiplied times some exponent. But keep in mind that there's e raised to some variable rather than a constant. So that's where you want to make sure you don't get that mixed up. But evaluating this integral is using the more direct way is actually going to involve a lot of use substitutions. And there's actually, in this video, I'm actually going to solve it a second way, and that actually uses the fact that this integral converges. And I'll explain a little bit more into detail once I get into that step. But actually following from that fact, we can actually write it in terms of limits, then actually use a bunch of use substitutions as well. I thought two of those methods were really cool, so I thought I actually, show this off in today's video. So yeah. Use substitutions for the win, am I right? Anyway, let's actually just jump right in. So let's start. This is the first method I'm going to do, and this, as I mentioned, this is going to use a lot of use substitutions. So first off, we're going to use u equals the square root of t. Then if I actually differentiate both sides, so that means du is going to equal 1 divided by 2 times the square root of t dt, but we can't really just plug this back in because we need to find something for dt on its own. So if you solve this out, then in other words, we can say that dt is equal to, just multiply the 2 times square root of t to both sides. We said that square root of t is u, so that would be 2u, then du. Plugging all this back in, so let's see, we have our, so the bounds remains the same when you plug those back in. So we see that if I plug u square, or let's see, so t, and then let's see, so it's square root of t. Yeah, so if you just plug t, so if you solve for t on its own, so you get u squared, so that means u squared, and then to the power -1/2, then multiplied by e to the -1985. So plug this, so t, so this is the same thing as before, so that means that would be u, that would have to be u squared, and then add this with u to the power -2, and then put in your differentials, your new differential dt, so tu, or 2u, and then du. And then if we simplify all this out, we'll get this simplified improper integral. So we have 2, then multiplied by e to the power -1985, and then multiply by u squared, and then add this with u to the -2 du. And so from here, here's a little note that we should put down, and that's mainly dealing with this the parentheses over here. We can say that u squared, and then add this with, I don't need the parentheses for this one, it's just a quantity on its own, not being raised by something. U squared, add this with u to the -2. If, in other words, you can actually write this as u, add this with u inverse square, and then add this with 2, okay? And so from here, we can actually rewrite things a little further for this integral over here. So actually, first thing is because there's a 2, so I can actually factor that 2 outside as that's just a constant. So 0 to infinity, and then over here, so it's e to the -1985. Plug this back in, so it's u minus u to the -1, then square. Add this with the 2, and then distribute this -1985 back into there as we replace that with the exponent. So now it'll become minus 3,970 du. Then in other words, we can actually see that e, using exponent rules, we can actually factor out this e to the power -3970 outside. So we have 2 times e to -3970, improper integral from 0 to infinity of e to the -1985, and then u minus u to the -1, and then square du. And so now let me actually let me also first denote that so far this is actually where we have that that's going to equal I, because the next thing we're going to do is actually not only just a use substitution, but there's also a little trick that we're actually going to be doing in order to solve the integral by itself. Well, for I mean. Then what I can do here is as performing another u sub, so I'm going to let u equals v inverse. And then, so if we differentiate this out, so du is going to equal -1 divided by v squared, then dv. Then if I just plug all this back in, so now our new form of I is going to equal the same thing, 2 times e to the negative 3970. Then if we, so actually we have our new bounds, so if we plug this back in, for u infinity, so that means that's going to have to go to 0, and then for 0, that's going to have to go to infinity. Okay, interestingly, that's nice because we have that negative. As we switch it, then that'll become positive, but I'll write this out in full before we jump into, further. So that means I have e, then -1985. So that means that will replace this with v to the -1, and then minus v square. And interestingly, you don't have to worry about the order because you can write this as v minus v inverse, then square, since the exponent is even, so it doesn't matter how it's commuted, it's still gonna get the same value, how you look at it. Then we have -1 to the v divided by v squared dv, put in that new differential for du. And so now what we have is, now just actually simplify all this out. So we have outside still remains the same. Then over here, so if I flip the bound 0 to infinity, it becomes negative. That negative will cancel. So I have 1 divided by v squared, and then multiply by e to the -1985. And then as mentioned, I'm going to put this back as v minus v inverse and then square. It's okay since, as I mentioned before, it's the evenness, then dv. How are we gonna do this? So we found that if by substituting a different variable, that we have that this form is going to equal this form. But as you take it, as you see, it's a dummy variable, so it doesn't matter how you look at this. What I'm gonna do here is I'm actually gonna take the sum of this integral over here and the sum of this integral, and then divide that by 2. So in other words, in a sense, it's like taking the average. So what this implies is that so 2i and then divided by 2, so I'm going to have I by itself again. And if I add these two sums and divide by it, for one, the 2's from here and here are going to cancel, and then by applying the linearity, because it shares with the same exponent, well, for inside the integrand, so I can actually combine this with linearity and say that this is going to be, from here, this is distributed with 1, and then add this with 1 divided by, we'll call this, we're actually going to go back into the world of x. So by applying all this, so we're going to have that the new integral, so this is going to be e to the power -3970, then divided by, or multiplied by the integral 0 to infinity. This will be 1 plus 1 divided by x squared, and then multiply by e to the -1985, then multiply by x, subtract x inverse, and then square, then dx. Again, we can actually now perform another u sub. I'm going to call this variable w. So we let w equals x minus x inverse. Then if I were to differentiate all this, so I'm going to have that dw is going to equal, now I'm going to group this in parentheses. So take the derivative, so this is going to be 1. And then the derivative of this is actually going to be minus 1 over x squared, so that'll change that to a plus. So 1 plus 1 divided by x squared, okay, then dx. Then put this back in, so now we have a new form of I. I is going to equal to e -3970 multiplied by the integral. So, okay, so we have to compute the new bounds over here. Where am I? Right here. So I have a plug infinity, so infinity minus 1 over infinity, so that's still going to be infinity over here. If I go to 0, so 0 minus 1 over 0, yeah, 1 over 0. So if you look at it that way, that's actually going to approach infinity, and that'll become negative infinity. And then now from here that we have e to the minus 1985, and then replace this with w, and then quantity square. And actually, I think I take that back. There's actually one more substitution. I don't know if I said that was the last one previously. This is going to be the last substitution. So one more substitution, we're going to let y equals w times the square root of 1985. Now that would mean that dy is going to equal, so it's just by itself, so dy is equal to the square root of 1985 then times dw. When we have to replace that dw by itself, we'll just divide that by both sides. And so we have that dw is equal to dy divided by square root of 1985. 5. And I can actually put this outside the integral, so that means now we would have that I is equal to e to the negative 3970 divided by square root of 1985. Multiply by this, the bounds won't change in this situation, thankfully. So from negative infinity to infinity, and so we have e, and then replace this, so that's gonna become minus, minus y squared, and then dy. And then interestingly, we know that as the assumption, I didn't write this down, but this is actually the Gaussian integral, so I'll just place this back, that's this equal to the square root of pi. Then actually simplify all this out, we get e to the power negative 3970, and then multiply by, and then use the rules with, square roots. You want to simplify this further. Multiply this by the square root of pi divided by 1985. And just like that, we have finished the first method involving a lot of involving a lot of use substitutions. But if you want to take this into the approach, this is more of the easier way. The other method that we will go to eventually, it's more of a, I guess it's like a hardcore, approach, if you want to put it that way. So other than that, let's actually move on to the second method. Okay, so now let's actually move on to the second method of solving the solution. And we're actually going to start with the generalization of this integral first before we can actually proceed forward with the details. So I'm going to say, we're going to suppose that for this function, I of A is actually equal to the same integral. This is actually going to be, so let's see, t to the negative 1/2, and then it's going to be e to the power negative a multiplied by t plus t inverse dt, with the condition that a is strictly greater than 0. The fact here is that this integral converges simply because the integrand over here is actually bounded by t to the negative 1/2 on the interval from 0 to 1, 0 non-inclusive, 1 inclusive, and then and by the other function e to the power negative a times t on the interval 1 to infinity, 1 inclusive. And so with this, we can actually write this, not only break this up into, into like a sum of integrals, but actually take it into the limit as well. So here we would have I sub I of a, and as we're gonna let the limit as y approaches infinity. So if we break this up, we're gonna have the integral from, so this is actually, again, doing this in terms of the limits. So as this approaches 0, that means this is actually gonna write this as 1 over y, and then we'll break this up from 0 to 1, or 1 over y to 1, of this integrand, same integrand listed above. So e to the power negative a, then t plus t inverse dt. Then we're going to add this, now continue on the rest of the way from 1 to infinity, replace that with y, of that same integrand as well. It's supposed to be t to the negative 1/2, and e to the negative a, t plus t inverse dt, and then we just close this off. And so what we're going to do here is we're actually going to take into pay attention to this integral over here. So what we're going to do is we're actually going to do a little bit of a substitution. So I'm going to let t equals 1 over u, implying that's going to have to be that dt is equal to negative 1 divided by u square du. And then we'd actually just plug all this back in. So here is going to be our new integral. So first off, we have to, change the bounds. So if I have 1 is equal to t, so that means u is going to equal, we're going to have that, the upper bound is going to be 1, and then on the bottom, so 1 over y, so that means u is going to have to be y. And then we just plug this back in, t is u to the negative 1, and then negative 1/2, then e to the negative a. Then if I just put this back in, so that means we have u inverse, and then add this with u, then put in our du, dt differential substitution, so like so, negative 1 divided by u squared and du. Then we can actually fix this up a little bit. For one, that we're taking the limit as it approaches infinity, so I can switch the bounds. That becomes negative. Then that negative cancels, and then if I just combine that u squared back in over here, so that means u to negative 1 times negative 1/2. That's positive 1/2. Subtract the 2, and then we're going to have this is going to be u to the negative 3 over 2. First, let me fix this. This is y, and then that's 1. That's going to be e to the negative a, and then u plus u inverse. I just switched. It's commutative under addition, so it's okay. Du. And so from here now, we can actually plug this back, substitute this back into this integral over here as, in something entirely new. And this is also interesting this is nice because we're integrating under the same, interval. So it should make things a little bit easier for us to work around with. So now we have this new limit slash integral. So we'll just put this back in. So I of a is going to now equal, so the limit as y approaches infinity. So now we're going to have the integral from, so this is y, 1 to y of, now I'm going back to the world of t again. This is actually just dealing with dummy substitution. So this is t, and then -3/2 e negative a t plus t inverse dt. And I'm just going to move on to the next line over here. Add this with the integral from same bound again. So this is t to -1/2, and then same thing, negative a t plus t inverse, and then dt. Just close off this this bracket over here. And now from here, now if I just undo that linearity and combine this under one integral, so now of course what we can do for one is that everything is in distribution with e to the negative a and so on. So I can actually combine these two sums over here. So we have the limit y approaches infinity, and over here this is going to be let's see, same integral 1 to y, and then t to the -1/2, and then add this with t to the -3/2, then e to the negative a t plus t inverse, and then dt. Now from here, then now we can actually perform yet another substitution. So let me actually move on to a different marker for this. So what we're going to do now is we'll let u equals this following parameter. We're going to let u equals a to the power 1/2 multiply by t to the 1/2, and then subtract with t to the -1/2. And if I just, differentiate both sides, so du is going to equals a to the 1/2, that's still, a constant. Then we're going to have 1/2, then times t to the -1/2. Add this, because that changes to a plus, that would be 1/2, and then t to the -3/2 dt. Then now I can do here is I can actually not only factor out the 1/2, but also divide the a over 1/2 to both sides, and divide that 1/2 as well. So now we have something new on the left hand side, and we'll get 2 times a to the -1/2, then du equals t to the -1/2. Add this with t to the -3/2, then dt, which is very nice because as we perform this substitution, this and the dt will disappear. We also have to be careful on how to rewrite the exponent associated with the e base as well. And also because we have 2 to the a to the -1/2, that's a constant, that's actually just going to go outside of our limit. So here, 2a -1/2, then we just multiply this with, and also another thing, or actually before I get to that, let me write everything out in full before I can jump to the next steps. So limit as y approaches infinity, and so we have to calculate the new bound. So if we calculate, so if I put 1 for t, that has to imply that that's actually just going to go to 0. And then if I plug in y, it's just this whole thing, except it replaces everything for t for y. So a to the 1/2, then y to the 1/2, then minus y to the -1/2. And then we have our new integrand, so e. And if you were to solve this out, we'll rewrite it in a way so that it preserves the equality for this exponent over here. We get that we can write that exponent as -u² subtract 2a and then du. And then what's nice is we have an e to the -2a, that factors that out because that's just a constant. So we have new is 2 times a, -1/2, then e to the -2a. And then now this is all that's left because, well, first let me put this back as the limit. Or actually, instead, now what we can do now, because of that, after I just did, now I can just take that limit as y approaches infinity, as we see over here. So we have that this is actually just indeed just going to approach infinity. So we have infinity over here and then a 0. And then now all that's left is just e to the -u² du. Interestingly, that's nice because, as mentioned, that I didn't write this down, that we can assume that that Gaussian integral we can use. But since this is from 0 to infinity, in other words, the positive real numbers, that's actually just half of that Gaussian integral. So it's just a square root of pi divided by 2 and just make that substitution. So we have 2a -1/2 e to the -2a, substitute this for the square root of pi, then divided by 2. And so indeed, if we simplify this out, we have that the closed form for I of a for a is greater than 0 is going to equal to the square root of pi divided by a multiplied by e to the -2a. And then all that's left to do is that because we found that closed form, all we have to do is just plug in 1985 to our generalization function, and that actually completes the value. And as you can see, that it's actually going to give it the exact value that we want, and just like from the previous method I showed. So plug in 1985 back here. So that means I have the square root of pi, then divided by 1985, and then multiplied by e times negative 2 times 1985, which is 3970. And so that means we actually just complete the evaluation that we wanted to show, just like the same thing from the previous. Call this a hardcore approach, and at least this is interesting to show it in 2 ways. So yeah, that's pretty cool if you ask me.